work, right? Okay. Welcome to the Carnegie Science Earth and Planets Laboratory Neighborhood Lecture Series. Get ready to explore how magma oceans shape planetary evolution in tonight's program, Goodness Gracious, Great Balls of Fire. As a reminder, to participate in tonight's live Q&A, please visit the URL on the screen at pigeonhole.at/magma or scan the QR code. Thank you for joining us. Your program will begin shortly. All right, I think shortly is now. Welcome, everyone. My name is Alicia Weinberger. I'm the Associate Director here, so I have the great privilege of introducing my boss, who is the director who's giving the talk tonight. So Michael Walter is the director of the Earth and Planets Laboratory, which is the research campus of the Carnegie Institution that is here in Northwest Washington, D.C. We've been on this campus since 1914, so I hope if you're joining us for the first time, you enjoy the evening, and if you have been here many times before, welcome back. We are dedicated to research and discovery in the Earth and planetary sciences, including exoplanets. And I think you'll see how that's exemplified by Mike's own research tonight. So we're very grateful to him both for the outstanding work that he does and also for being such a leader in our department. So I'll give you a little background. Mike received his Bachelor's of Science in Geology from the University of Nebraska, which has always struck me as an odd place to do geology, but maybe you can tell me that's not the case. And then his PhD in geology from the University of Texas at Dallas. And since then, he has traveled the world for his research. So after postdoctoral research at the University of Alberta in Canada, he made a great decision to come here to the Carnegie Institution's Geophysical Laboratory, as it was then called. And he was here from 1993 to 1995 as our postdoctoral fellow. And we still have about 8 new postdoctoral fellows who join us every year, plus many more who are brought by our staff scientists to do research and to hone their skills in science on this campus. So we're always happy when they go on to bigger and better things. He then spent 9 years in Japan and 14 years at the University of Bristol in the United Kingdom before we were lucky to lure him back as director of the Geophysical Laboratory, predecessor department for the current Earth and Planets Laboratory. And he came back here in 2018. And in 2020, we became the Earth and Planets Laboratory. And in 2022, he became our director. So Mike is a petrologist, which is a scientist who studies how rocks are transformed on the Earth and how our 4.5 billion years of Earth's history are manifested in the rocks that we can observe. He does experiments, he does theory to try to understand how they melt, solidify, and get transported. He has many awards, including the Bowen Award of the American Geophysical Union, which is a top recognition for a scientist in petrology. He's also a fellow of the American Geophysical Union and the Mineralogical Society of America. So I would just quote from his citation for that Bowen Award, where another great petrologist wrote, "Mike Walter asks the important questions and gets the right answers." So tonight he'll tell us about a class of special pools of melted rock known as magma oceans. And so it's my pleasure to introduce his talk, Goodness Gracious, Great Balls of Fire.
Oh, thank you so much, Alicia. Yeah. So welcome and thanks everyone for coming. There is some great geology in Nebraska. It turns out that we would go on our field trips down to downtown Omaha and look at the rocks on the buildings. Great exposures, well polished, right? But yes, I'm a little hot. I think it's the glow from the magma ocean. I might have to take this coat off in a little bit as we warm up with tonight's talk. This is a subject that in one way or another I've been working on, and a lot of colleagues at Earth and Planets Laboratories have been working on for my whole career. And especially beginning when I was a postdoc here, I started doing some experiments that related to understanding how a core forms in a magma ocean, and we'll see a little bit of that in this talk. And I'm not going to talk so much about my research tonight as I am just to give you a narrative about magma oceans and why they're important, and why you might. How many of you have heard of a magma ocean before tonight? Okay, there's a few of you. That's fantastic. You know, you're not going to buy beachfront property at a magma ocean, but they were important a long time ago, and they remain important. And as we'll see, I think I have one slide. As we look out into exoplanetary systems, some of the planets that we see are molten objects. Okay. Oh, I have a clicker right here. All right, so let's get going, or not. Maybe I have to instigate it here, or maybe I have to turn this on. It was the turn on thing. Okay, so in this slide, I make a statement and ask the question at the same time. Differences in terrestrial planets are related to their birth and infancy. That's a statement, or it could be, are differences in terrestrial planets related to the birth and infancy? And I would say mostly yes, although it's not entirely clear that all these differences relate to that. There's also 4.5 billion years of planetary evolution involved. So here's our 4 terrestrial planets, and we're gonna concentrate on them tonight. And this is some artist's schematic of what the interiors of these objects look like, and you see they're quite a bit different. They're all rocky planets. They all formed by accretion in the inner solar system in the first 100 million years or so of our solar system, but they turned out a lot different, even though they're made of basically the same stuff. Here's the Earth, and you see that inside the Earth we have a lot of convection, and we have plate tectonics on our planet. It's a very dynamic planet. We have a core that's mostly molten, and it has a small inner core that is solid, and the core convects. It generates our magnetic field, a very strong magnetic field. That is one of the reasons that we have life on our planet. And we have a water ocean. Venus, on the other hand, is right next door, about the same size. We think it's basically the same composition. Doesn't have a water ocean, has a thick CO2 atmosphere. It has a core that is, we think, fully molten, but it doesn't have a magnetic field. It doesn't have plate tectonics. It has some sort of tectonics that we don't understand, and it has a surface which is covered with lava that resurfaces itself every 300 or 400 million years, we think. We don't know a lot about Venus. Our planet, of course, has a moon as well, a primary moon. Mars has a couple of small moons that are probably captured asteroids. Mars, on the other hand, is a smaller planet. It has a core. I'll talk to you a little bit about what we know. We know more about its core from a recent mission. And it probably had a magma ocean. Not entirely sure, but almost certainly did. And it doesn't have plate tectonics. It doesn't have an atmosphere. It doesn't have a magnetic field. We have Mercury, which is a very strange planet. This kind of looks like a brain, but I think it's supposed to be metal. And it's because it has a really large metallic core. So all of these planets have cores that are about 30% of their mass. Mercury has a core that's about 70% of its mass. And so we're going to just kind of look at these differences through the lens of what was happening early in the evolution of these planets. Okay, this keeps happening. I'll just do that. Oops, I'm getting way too far in. There we go. Okay, and it all starts out with accretion. And so this is a whole field in and of itself. And you could have several talks just on this subject, but we're going to wrap this up into about a minute narrative of how the planets first accreted. And what you're seeing on the left is an artist's rendition of a protoplanetary disk, a planet formation disk, a nebula, that has a lot of gas and dust. And this is actually an ALMA image of a nascent disk in HL tau system. And to me, it's just like nature mimicking art, right? Or I'm not sure, maybe it's the other direction. This was probably first. I'm not sure how old that image is, maybe 10 years old. But the idea here is that you have gas and dust, and the dust essentially begins to coagulate into larger and larger objects that are maybe meters and then 5 meters, and these things start to run into each other, and they grow larger and larger objects until they become what we call a planetesimal. And a planetesimal is something like 50 to 100 kilometers in diameter. And once those planetesimals form, they start gravitationally interacting. And some of those are going to be a little bit bigger than other ones. And turns out the big ones, they rule the day. So they have a little bit more gravity, so they start attracting more stuff. And the little ones, they all lose out. They all start glomming onto the big ones, okay? And what happens is that the bigger objects start to carve out what we call their feeding zones. And you can, and this is based on theory, and this is what you see. You actually see this when you look out into these planet-forming regions, that you can see that there's some objects in there that's carving out a zone and growing larger. And the idea here is that after, you have thousands and thousands of planetesimals, and they start to grow into larger and larger objects, and you end up with, I don't know, some dozens of planetary embryos. And these are maybe hundreds to thousands of kilometers in diameter. And the late stage of the impact, after the gas is cleared out and most of the dust is now cleared out, these big objects start to interact with each other, and they start to have giant impacts. And we'll talk a little bit about what happens there, the consequences of those impacts. Early planetesimal differentiation. What does that mean? Okay, so we have these objects, and these are actual objects in our solar system. So this is Ryugu, which is an object that the Hayabusa spacecraft just recently visited. We have a sample from that, which is so cool. We even analyzed some of that material here. This is a very primitive object. It's very small. I'm not even sure it qualifies as a planetesimal, but it's remained. It didn't get consumed by the planets as they grew, and it's undifferentiated, meaning it's basically just a pile of rubble that came together, and it never melted. Nothing ever happened to it. It's still got like ice and carbon and all these other volatile elements in Ryugu. So this is what we mean by undifferentiated. Objects that are differentiated, it means that they've undergone a process which has changed their interior in some way, and that is usually or oftentimes melting. And it allows segregation of crystals. It may allow a core to form, and you end up with sort of a layered object. And that's what I mean by the word differentiated. And that differentiation is primarily driven by heating. Okay, that's the main thing that drives early differentiation of these planetesimals. This is the asteroid Vesta. It's in the asteroid belt, which is between Mars and Jupiter, about 2.5 AU, or 2.5 the distance from the sun to the Earth. It's the second largest asteroid and makes up, I think, about 7 or 8% of the mass of the entire asteroid belt. So this is a relatively large object, 260 kilometers, very typical of what we think a planetesimal was like when they were accreting, and it's differentiated. How do we know that? We actually have meteorites from this object. We have meteorites from the surface. We have meteorites from the interior, and this happens when an impact. Even now, the surface it gets run in by other objects, and it spalls off some material, and those materials end up on Earth. And we know that because we can take a spectra from the surface and we can match it very closely with the meteorites that we have. Okay, so we've been able to study this object in quite some detail, and it represents one of these fully differentiated objects. It has a core, it has a molten lava-covered surface, and it has a differentiated mantle. And this plot just shows differences that you would expect. There's a whole range of possible outcomes, from undifferentiated like this, fully differentiated like Vesta, and kind of everything in between. And this depends critically on how and if and how much the planetesimal melted. Why would they melt? Okay, there's a couple of reasons. This is a really important one. short-lived radioisotopes in the early solar system. So what do I mean by that? There's a couple that are really important. One of them is alumina-26, so this is an isotope of aluminum, and it has a half-life of about 0.7 million years. So it's radioactive, it decays away to another isotope called magnesium-26. That happens through, it loses an electron from its nucleus, a neutron creates a proton, it has the same mass, but its proton number changes, so it turns into a different element. And it has this very short half-life. And so this element was injected into our solar system very early on, when the solar system was very young, basically T0, and the clock starts at that point. And the way these radioisotope systems work is that the rule of thumb is that they're alive for about 5 times their half-life. And so we can detect whether this was alive for about 3.5 million years, roughly. There's another one called iron-60 that converts to nickel-60 by beta decay and has a 2.5 million year half-life, so roughly 12 or 15 million years it would be around. And these were in our early solar system. And so these early objects that accreted would have accreted these elements as well, and they produce heat when they're decaying, okay? And they're alive at this earliest part, so we can use them to do a couple of things. One is we can predict how much heat they would produce in an object, and two, we can date things by looking at their daughter products. And this is just an example from a particular meteorite called an achondrite. This is its number. And the way this works is you measure the magnesium-26. It's the kind of thing that we can do in our isotope geochemistry labs here. And this is what that meteorite is made of in terms of different minerals. And each of those minerals captures a little bit of different ratio of aluminum to magnesium. And so when the clock starts, the amount of magnesium that gets produced in these individual minerals is different. And some have more. The ones that had a higher aluminum-magnesium ratio produce more, and the ones that had a low produce less. And they all fall on a line, and that line gives you the age. And in this case, the age is about 4.564.8 billion years, okay, which is a pretty precise age, and means this object was around in the first couple of million years of solar system evolution. Now, this heat that is produced by this decay, so what this does is it proves that we're onto something here, that it's important to understand the effect of heating in these early objects from the decay of these short-lived isotopes. This is just some modeling that you can do to say, well, how much would it heat an object? Well, it depends on 2 things. It depends on the size of that object, which is on this axis. And the reason is because if an object's too small, the ratio of the surface area to the volume of that object is quite large. And so it loses its heat too. It just can't heat up, okay? And so it needs to be big enough to kind of hold the heat in, which is about 50 kilometers or so in terms of its radius. And then this elapsed time means if that object formed 1 million years after the solar system began, then alumina and iron have been already decaying for 1 million years, so there's not as much of it left, and so it won't have as much heating impact on the object. And so this is just a numerical model that shows for these kinds of planetesimals in this range, and here's Vesta out here, and here's our really small object out, and this explains why this one's molten, this one's differentiated, and this one isn't, right? Because this one was large enough to retain heat. It would have melted to a large extent, maybe up to greater than 50 or 60 or 70%. That's a magma ocean on that early object then. And this is only based on alumina-26, this modeling, not even including any iron-60 in the decay. So that would mean even more melting. But this object, very small, never had a chance, okay? So that's one way that we make magma oceans in these earliest objects, and we differentiate early objects is through decay of these short-lived isotopes. How do we know this happened? Okay, and I love this because this is like forensics of the early solar system. You know, you have these models, but you have to be able to test them. Otherwise, they're just kind of creative models. We're going to look at another short-lived radioisotope. This time, it's the hafnium to tungsten system. Hafnium-182 decays to tungsten-182, again by this beta decay, losing electron from its nucleus. with a half-life of, in this time, about 9 million years. And so it's extant for, 50 or 60 million years or a bit more. And it's a probe, especially of core formation. And why is that? And a probe of differentiation. The reason is because hafnium is an element that does not like to go into metal. And the cores of these objects are metal. The metal segregates, they're iron metal, they're iron rich, and hafnium does not like to go into that metal, but tungsten does. So if a core forms early on a planetesimal while this isotope is still active, that hafnium to tungsten ratio is going to change hugely, depending on whether you're in the metal or whether you're in the silicate. And when it changes, that gives us a chance to find evidence for that change. And we do that by measuring meteorites, iron meteorites, silicate meteorites, and meteorites from the moon and Earth and Mars, not Earth meteorites, but Earth directly. Nothing from Venus and Mercury, unfortunately. And then we measure that ratio in a mass spectrometer like we have here and relative to some standard, and we say, okay, is it like primitive material or is it not like primitive material? So I'm going to show you the answer to that. You'll probably guess what it is. Well, the way this works, just to take you through this a little bit, is imagine solar system forming right here. Maybe there's some period of time that the object hasn't differentiated yet, but imagine that right here, Vesta, for example, underwent heating and melting due to alumina 26 and iron 60 decay. Okay, so now it differentiates, and it differentiates, what it allows is that core, is that metal to melt and percolate to the center. It's dense and just doesn't want to be out there in the outer parts of the planet, but if the planet's not melting, it's kind of trapped. But once you melt it, it's really easy to move that core inward. And so this, let's say, too much, there we go. When this happens, the silicate mantle will have a very high hafnium-tungsten ratio. The core will have a very low one, and so we can measure that and get an age and just evidence of when that had happened. And sure enough, when you go look at samples, these are iron meteorites. And okay, this is the primitive meteorites. What I mean by that, remember that little Ryugu? That is a primitive composition that never differentiated. Okay, there's a whole suite of meteorites that are called carbonaceous chondrites. And they're the most primitive, undifferentiated material that we have in our solar system. They represent kind of the first building blocks of the stuff that eventually made up the planets. And there's kind of a whole range of those. And they measured a whole bunch of those and found that, okay, this is where they belong. So that's kind of like everything in this region would have had that tungsten value. Don't worry about what this means down here. It's just the tungsten isotopic composition. Then they measured iron meteorites, and sure enough, they're very low relative to that. So this reservoir here continues to grow along this path, but if you have differentiation and have an early core, then that core doesn't grow anymore, tungsten. It just sits there forever at the same tungsten isotopic composition. And so it's different. There's a difference between the primitive reservoir and the core that formed early, and we can see that. And that is so cool that you could actually take an iron meteorite and measure this thing and have this hypothesis that, well, you might be able to see that it formed early, and sure enough, you find that out. And this means it formed within the first few million years of solar system formation. So planets were already differentiated. They already had magma oceans in that earliest stage. Oh, and this is the Earth's silicate mantle, and it's a bit positive, as it should be. And you can actually do some modeling of that, and you can tell the timing of formation. You can constrain the timing of formation of Earth's core. And when you do that, and you do it for all the different planets, what you find is Vesta is it formed very early, within a few million years of core formation, and this is as a function of planet radius. Mars formed a core later, around 10 million years, a bit more perhaps. Ursa appeared around 30 million years. And what do you notice here? the moon and Earth have the same core formation age of around 30 million years. Why do you think that is? The moon kind of came out of the Earth. They formed together. Whatever happened that's being recorded there, it's because the Earth-Moon system, they formed as a system, and we'll get back to that. So this is actually sort of evidence that these objects all had magma oceans, because you really can't form cores unless you did. And this is probably tracking the time that the accretion time scales of these larger objects. So you notice that the Earth is way up here and Mars is down here, but Earth is bigger. It took longer to accrete. And the core formation that's being recorded by this number, it's not that the Earth just all of a sudden at 30 million years said, okay, now it's time to form my core. The core was actually forming progressively throughout, and you're kind of getting some kind of average there. Okay, another way to melt, and this is much more violent. I was talking about those giant impacts. So what happens when two worlds collide? No one survives. There's a song. These are some simulations. On the left here is obviously an artist's rendition. And over here on the right is a simulation of the moon forming giant impact. So this is the sort of paradigm for how our moon-Earth system formed, that there was a late giant impact, and the moon formed from the material that resulted in that impact, or resulted from that impact. And so here's one of the models by Robin Knoop. Get that to go, and there's the splashdown, and it is colored for temperature, okay? And I don't have a scale on here. It's kind of fun to watch this as the stuff kind of slinging out at you on the page, and you'll kind of see some an object form here. There went something flying by. There's a proto-object, that little yellow dot, but watch what happens when it comes around. It gets all strung out. That's just kind of fun to watch. But what these models show and what they predict is that the Earth would have been up to 10,000 degrees Kelvin. And if that's the case, it is entirely molten. So it's very likely that after the moon forming impact, which we think happened relatively late, like around 70 million years, that the planet was, so whatever happened before that was almost erased in some sense, and the Earth was entirely molten. Now, we're the only planet, terrestrial planet, that has evidence for this giant impact, except for maybe Venus. Venus doesn't have a moon, but what you may not know is that Venus rotates the other direction. And so one theory is that Venus did have a giant impact. It didn't form a moon, probably because of the details of the impact and the angle at which the impactor and Venus might have hit. Not all outcomes end up in moons, but it may have knocked Venus 180 degrees, right? So it's completely the other direction. See, Alicia's a little bit skeptical of this. Venus also has a very, very long day, 243 days. I think that's about right. So it's very different in terms of its spin and its spin axis than the Earth is, and that may be a result of one of these giant impacts. But the takeaway here is that this was a very violent beginning, and irrespective of anything else that happened before that, Earth was completely molten at one point, or perhaps almost completely molten. A very interesting model that is more recent that comes out of this is, I won't go into too much detail, but the model that I just showed you has some problems. And the problem is that it predicts that most of the moon is made out of the impactor, which is some kind called Theia, impactor Theia. And that doesn't work very well because it turns out that the moon and the Earth are almost identical in terms of a whole number of isotopic and chemical fingerprints. And so Sarah Stewart and her coworkers came up with a different model for this giant impact, where the objects were spinning really, really fast. So the Earth before the impact was spinning at a rotation rate of about 2 hours, and the impactor also spinning very fast, and they smack together, and the angular momentum of the whole system is very high, and they're spinning very rapidly, but eventually they slow down because of a resonance between the Earth and the Moon and the Sun. But the important part of this is, they can kind of get it all right, the important part of this is that the model predicts that when you do that, you form this weird looking donut-shaped object, which they call a synestia. And it only lasts about 100 or 200 hours or something like that. But what it is there's a hot molten proto-Earth in the middle. It has a gaseous vapor envelope and molten material outside of it. That's the synestia. And the Moon forms within that. And as it shrinks, the Moon eventually emerges out of that. And it also was probably completely molten. So this is very much theory at this point. A synestia has never been observed, but there's no reason that we shouldn't be able to observe one if they actually exist. But they do come out of the theory. And these synestia can also explain this strange chemical similarity between the Earth and Moon that the other model doesn't. This is just one example. This is oxygen isotopes. You don't really need to worry about this as oxygen 17 on this axis, oxygen 18 on this axis. These are Mars meteorites. This is what Vesta looks like. If you look at other objects in our solar system, other meteorites, they kind of plot in various places on here. But the Earth and the Moon fall exactly on the same line. So you really need a model that can explain that. And there are some other isotope systems like tungsten, for example, which isn't a volatile element like oxygen, but very refractory. And it also has the same composition on the Earth and Moon. And this sort of synestia can potentially explain that, this really hot early state where everything was either molten or vaporized. Okay, so another important factor with these impacts in magma oceans is that they produce the earliest atmospheres. So you can imagine you've got now this object, it's totally molten for whatever reason, decay of isotopes, energetic collisions. It begins then to degas. And so proto-atmospheres are going to be forming around these earliest objects. And the atmospheres of Mars and Earth and Venus and Mercury are all very, very different. And one of the things that we're trying to understand is why that is, okay? And so part of that puzzle is definitely going to be related to this magma ocean stage. And I won't go through this in any detail. It's completely schematic, but imagine that the Earth was totally molten. Maybe, maybe not, a nebular gas was still around. It depends on how quickly the Earth formed. Probably for Earth, by the time it got big, the nebular gas was long gone. But the accretion, the material itself that was accreting will have had volatiles in it, things like water. We know that. We have an ocean of water on the surface. So we did get volatiles delivered to our planet in some way. Turns out that magma oceans can store an unbelievably large amount of water and other volatile elements as well. The solubilities at pressure are really, really high. At low pressure, it's very low, which is a really interesting thing, because what that means is that if you've got a lot of water inside this magma ocean and it's convecting, as it moves towards the surface and gets to low pressure, it's going to emit that water. It's going to exsolve that water, and this is one way that you form an early atmosphere or a proto-atmosphere. It may have been that hydrogen was very important if a nebular gas was around. In some objects, in smaller objects, you can imagine that you still had the nebular gas around. Hydrogen dissolves in the magma ocean. It reacts with things in there. It goes into the core. It creates FeO. It can create water. We're doing a lot of research at EPL right now. One of our scientists, Anat Shahar, in particular, is really working on this, try to understand the complexity of magma oceans and early proto-atmospheres. This is a figure from Anat's paper with Ed Young and others. And basically what is being posited here is that you have a magma ocean stage, and this could be a generic planet. It doesn't have to be Earth, it could be any planet. You end up with a primary atmosphere, that there's a whole series of reactions that happen as the magma ocean is both dissolving the atmosphere and as the water and the carbon and other things are reacting with the magma. And you end up with a planet that looks maybe something like Earth. Now, there's something I want to, this is a little bit complicated, but we'll get there, is that as this is happening, there's this thing called oxygen fugacity. What does that mean? How many of you remember fugacity from chemistry? Okay, very, very few of you. You probably ejected that from your minds as quickly as possible. The way to look at it is how much oxygen is available to bond with other stuff. It's not locked up oxygen, it's kind of free oxygen. You can think of it as the activity of oxygen, or you might think of it as the partial pressure of oxygen. In a thermodynamic sense, that's exactly what it is. And we think that the earliest materials, for example, on Earth, were very reducing, meaning the oxygen was all locked up, really couldn't do much. And as the planets continued, they got more oxidized. Our planet now, Earth, is a relatively oxidized planet, and we're trying to figure out how it got that way. And magma oceans are one of the ways that it could get that way. And I'm going to show you how now. Oops, didn't mean to have both of those up at the same time, but that's what we get. So look at the left side over here. And why is this important? It's important because the composition of the earliest formed atmospheres, which may be very critical for habitability and how the planet's atmosphere develops through time, may be dependent on this thing that we call the oxygen fugacity in the magma ocean, all right? And this is kind of shown over here. This is depth. We know what the oxygen fugacity is right at the boundary between the base of the magma ocean and the metal. Okay, take my word for it. What it is we know we have metal in equilibrium with a silicate at that pressure and that temperature, and we can calculate an FO2. It's very reducing because metal's there, okay? The question is, as you go up towards the surface, how does FO2, how does this oxygen activity or partial pressure change? And this is a very active area of research. We have a talk here on Thursday from a scientist named Jay Deng, and this is his work right here where he's calculated this. This is all from first principles. I've been doing experiments with colleagues on this, and I very much wanted to show you the results, but we're not quite ready for prime time, especially since we're projecting out on YouTube. So what you're seeing on this diagram over here is pressure within the magma ocean. So this is going down with depth. This is where the Earth's surface is now. And this is where the Martian surface is now. And this is where the moon surface is now. And if you had a magma ocean beneath a surface that had those types of FO2, this is this oxygen fugacity, oxidized on this side, reduced on the left, then the magma ocean is calculated to take these kind of profiles. And sure enough, you can get right to what you need to be for Earth. Iron-Weisstein -2 is about what we think is at the core mental boundary today. And this can explain the oxygen fugacity of the atmosphere. So this is why Earth early on, we believe, had a very H2O and CO2 rich atmosphere. It's an oxidized atmosphere. If it would have been very reducing, we'd have had things like hydrogen. We'd have had CO, and these are all things that are not very palatable for the origin of a habitable planet. And you might be able to, because of the difference in size of the magma ocean and the planets, you might be able to explain the difference in the atmospheres of different objects like Moon, Mars, and Earth just from the size of the planet based on the depth of its magma ocean. So again, the magma ocean is controlling so much of the initial state. Core formation is part of the magma ocean process. First, crystallization of a crust is part of it. Formation of proto-atmospheres and kind of establishing the way that planet is going to evolve, all is due to the nature of the magma ocean. Okay, so that's kind of the primer on magma oceans. And we're going to get back now, and we're going to look a little bit more pretty rapidly at each one of these planets and what we can say about whether or not we think they actually give evidence of a magma ocean. So this is kind of a lot of speculation at this point, but shouldn't there be like really, really hard data. We've seen some of it in terms of the hafnium and tungsten isotopes, that small objects definitely differentiated early. Probably means they melted and had magma oceans. What about our planet? Okay, lots of points on that diagram. What you're seeing over here, this is temperature on this axis. Actually, it's condensation temperature. And what that means is, what would the temperature with these elements condense out of a gaseous nebula? Okay. Everything over on this side of the diagram we call refractory. Oh, there we go. And everything on this side we call volatile. We're going to concentrate on these elements right here in red for our story right here, okay? And these are called siderophile elements, things like nickel and cobalt and iron and molybdenum and tungsten. And the reason they call that is because, again, they like to go in the metal. So when a core forms, they're just going to almost wholesale go into that metal core. Everything that we have now, all of the nickel and cobalt that we mine at the surface is left over from what went in the core. Our core is about 5% weight in nickel. So if you want to mine, you want to go to a place that has a lot of nickel for mining for our cell phones and things, that's where you want to go. Pretty impossible. So you see here over here, nickel, tungsten, molybdenum, cobalt, platinum, these are all in the core. And all these other things out here like magnesium, silica, calcium, aluminum, sodium, potassium, they make up rocks. That's what, you go out and pick up a rock, that's basically what they're made of. Hafnium, rare earth elements. And it turns out that this difference between this number, this one here, this is what we would expect for this primitive material. The most primitive material, this chondrites. We're normalizing our planet to that. We're going to say, okay, that's what we started with. Now let's look and see how much we have in our crust, in our mantle, and compare it to that value. And when you do that, you find that all of these are depleted relative to primitive material. And that's because they're in the core. All this stuff's in the core, and that's why they've all moved down relative to that line up there. Now that gives us the opportunity to say, can we use that pattern to predict the conditions of core formation? And it turns out that you can. This is actually something I worked on when I was a postdoc here all those years ago, and a couple of the points on this plot actually were produced here 30 years ago in the lab across the way. And what this is showing you is, this is pressure. So these are high pressure experiments that we do in the lab. Go to really high pressures, go to really high temperatures, mix up a little bit of what we think the bulk Earth is like, right? And we see that we create a metal blob and a silicate melt. So this is at high pressure and temperature, this was a silicate melt, and that would kind of represent our mantle and crust. And this is a big ball of metal, and that would iron metal, and that would represent our core. And then we can go in and we can measure how things like nickel and cobalt partition between those two. They just don't go equally between those two. The nickel and the cobalt favor the metal, and we can say, well, how much do they favor the metal? And that's what we call a partition coefficient. And that's what's shown on this on the y-axis here. And what you see, the important message here, is as you go to higher and higher pressure, they become less and less siderophile. So if they really like the metal, they have a very high number here. If they don't, they're lower. And so pressure makes them go down, and it makes them about equal to what we measure in the mantle at about 40 GPa. That's a depth of about 1,500 kilometers. So what this tells us is the pattern that we see in those siderophile elements gives us an indication of the depth at which the core and the mantle equilibrated. And it's very high. That is prima facie evidence for a magma ocean, because there's just no way that you're going to get that kind of depth of segregation unless you have a planet which is melted very, very deep, okay? Now the core form, now this works actually. People have been working on this for 30 or 40 years, and we've marched through a lot of these elements, and it works very well for that whole group of siderophile elements. And when you kind of put the models together, you end up with an average pressure of core segregation for Earth of about 40 GPa, plus or minus 10. There's uncertainty in these models. The core mantle boundary today is way down here at 130 GPa. And so one of the ideas was, well, the average pressure that you're getting was because the iron metal last equilibrated when the silicate mantle was partially crystallized, and you had this big sort of iron pond at about 40 GPa. I don't think this is a right model, even though I'm one of the co-authors of this paper, because I think it's too simplistic. It was probably a much more dynamic process, and you're probably getting some average pressure of equilibration. But irrespective, it really shows that the Earth once had a deep magma ocean. If we do this for all of the different planets, this modeling of the siderophile element abundances, because remember, we have meteorites from Mars, we have samples from the moon, we have meteorites from Vesta. What you find is they all show this indication of core formation and equilibration at high pressure. And again, that is a signal then that all of these objects once had magma oceans of various depths. So they all started kind of in the same way. So Mars at about 10 GPa, Moon, these are smaller objects, so their internal pressures aren't nearly as high at a few GPa, and Vesta basically at zero pressure. So if you have one take-home message about proof that that we can actually detect that there were magma oceans on these planets, this is it. Okay, the core formation and the signature of core formation in these siderophile elements provides that. I'll go just very quickly through this. We don't have a lot of evidence from the silicate part, except for this business of core formation, for crystallization of the magma ocean. You might expect that if we had a big magma ocean, that you would segregate dense crystals and they would float to the bottom, and you'd segregate another crystal and another layer. And when you do that, you would change the chemistry relative to that primitive chemistry that we call, that we normalize to, that chondritic chemistry. And you would see that easily in the silicate rocks. We don't see that on Earth. And the reason we don't see that is because we have plate tectonics. And the mantle's been stirring for 4.5 billion years. And any of that early information of crystal segregation in the magma ocean is mostly lost. I won't go into the details. There are some indications from various chemical and isotope systems that look like we can see some early domains, but it's a bit complicated and would take too long. But here's one which is kind of interesting, and that is, how would the magma ocean have crystallized? So here's the melting curve for the mantle, okay? Here are what are called mantle adiabats, and what that means is if you just had a temperature profile of the mantle and the change in temperature is only because of pressure release, it's just like our atmosphere. You've probably heard of the atmospheric adiabat. You go up, it gets colder. Same exact principle for the mantle, and that's what these lines are. As the mantle cools, you'll notice that it hits its melting curve, or its crystallization curve. It starts to crystallize at these temperatures. It hits it in the middle of the mantle, not at the bottom. And so the models are that the mantle crystallized from the middle outward, which is kind of cool. And you may have ended up with a basal magma ocean layer. And so at the end of it, this would become very iron rich and dense. And you end up with what they call these remnant crystal piles. And these are dynamic models. This isn't just cartoons. This is a cartoon. But these are based on sophisticated geodynamic models of how the magma ocean would crystallize and what would happen as it did so. And the prediction is that you end up with these big sort of dense crystal piles at the base of the mantle. And you end up with these partially melted zones that are probably still partially melted today. And it turns out that we actually see evidence for something like this from seismology. And what we see from seismology is that there are a couple of big sort of mountains on the core mantle boundary that extend up hundreds of kilometers. And we can see that because this is a map of the core mantle boundary in terms of seismic velocities. And what we find is that this is the scale for the color on here, and the red is slow and the blue is fast seismic velocities. That's how rapidly those earthquake waves are moving through the material, okay? And what we find is at the base of the mantle, we have these two big low velocity regions, and they've been named Jason, after Jason Fitzmorgan, and Tuzo after Tuzo Wilson, who were two of the main inventors of plate tectonics, which I think is kind of cool. They would appreciate that. And so this may be evidence. We're really working hard on this now. That these are called large low shear velocity provinces, and these are these red areas here, which we think may be partially molten, or possibly not, are ultra low velocity zones. They have really, really low velocities, and they may be remnants of this magma ocean stage. Okay, that's just me saying, but most of that would get stirred away because of plate tectonics. All right, how about the moon? The moon has really good evidence for a magma ocean, right? If you really want to step out and say, okay, here was a place where there's magma ocean, it's the moon. So you see over here, this is a cutaway of the moon. This is actually a picture of the moon's surface. Black areas are relatively younger basaltic outflows, that's why they're black, and the white area is a rock called anorthosite. How many of you were here to see Steve Parman's talk a few weeks ago or a couple of months ago? He talked a little bit about this anorthosite as well. Anorthosite is a rock that is made of a mineral called almost 100% plagioclase. So when you pick up a granite and you've got the white minerals in those in the granite, that's plagioclase, okay? And so that there's a huge amount of this plagioclase at the surface of the moon. And when they first brought some of the first samples back from the moon, this was very curious. And in fact, this is really where the idea of magma oceans began, was trying to explain all this anorthosite on the moon. And the way they explained that was because we knew at the time that relative to a magma, the plagioclase crystals have low density and they'll float. And so the model that was put forward, 1970, was that this is a flotation crust. And in fact, the moon was completely molten or mostly molten, and the plagioclase starts to crystallize and it flows to the surface, and the other crystals, olivine and pyroxenes, they form at that depth. It's a bit more complicated than that, but that's a pretty good cartoon. Oh, and this is just what an anorthosite looks like. So it's a very white rock, and that's why the surface of the moon has that color. We can also see it in the chemistry, which I think is fantastic. So you bring these rocks back of different kinds from the moon, and there's one in particular that's called creep. And creep makes up relatively large domains on the near side of the moon. And what creep means is that these are rocks that are really enriched in potassium, in rare earth elements, which are all these elements down here, and phosphorus. And when you analyze these creep rocks, what you find is that relative to our model of what the whole moon is, or you could put whole Earth, or you could put chondrite there, whatever you want, these are tremendously enriched in these elements that like to go in magmas. They like to be in melts, okay? But they're depleted in this one element. This one element is europium. Now, it just turns out that plagioclase loves europium. Doesn't like any of these other things, but it has a real big appetite for europium. And so this is unbelievably great evidence for the fact that you had this plagioclase flotation crust, and that the source region of the creep magmas that came later were melting of that material that had already seen this plagioclase flotation crust. So you go to a highland crust, and you can see the other side of that, the complement of that plagioclase flotation. And you go to the basaltic regions, these dark mare regions, and you can see they're also depleted they also show the evidence of this plagioclase flotation. So again, the moon, fantastic evidence that there was a magma ocean. I won't spend a lot of time on Mars. I think I just have this one slide. This is really recent data, and this came from the InSight mission. So how many of you heard of InSight? So InSight was a mission where they actually put a seismometer on the Martian surface, just one. Right? So they have one seismometer sitting on the surface. It was active for about 4 or 5 years, and I think it lost its battery life, maybe got covered in dust or something. But during that time, they were able to take seismic recordings from moonquakes. So every now and then, a bit of shifting on the moon acoustic waves travel through the planet, it's picked up by the seismometer, and they can make inferences about what's happening inside. And some of the first data that came back, and they started getting more and more data, and some of the first results were, wow, the moon's core is huge, much bigger than we thought it was. And the problem with that is that you couldn't really explain the size of that core with any of our models for what the chemistry of the core should be. It was just too big. So they looked more closely at the data, collected more data, and they used these P waves, they're called, compressional waves, and they looked at how they both reflected and refracted in this region right at the top of where the core is. And they said, actually, that's not core at all. That's silicate magma. There's a melt layer that's about 150 kilometers thick at the top of the core, and that's very likely a remnant from the Martian magma ocean. So kind of like our planet, we're at the core mantle boundary. We see this evidence for the last dredges of a magma ocean. We see the same thing potentially on Mars. And finally, we'll look at Mercury very quickly. And Mercury is a really strange place for so many reasons. And it has this really large core, for one thing, way larger than you should be able to have a planet have given the compositional models we have for the material that's kind of collecting to form these planets. And so the model, I think, that is most prominent about how Mercury got its large core was that there was an impactor that stripped off a lot of the silicate. So again, depending on the details of the impacts, you can get a lot of different kinds of outcomes. And in this one, the idea is that most of the unaccreted ejecta was silicate, and it just never was accreted back onto the planet. And so that left the planet with this big core and left it very hot as well. So it had this magma ocean. Bit of a complicated diagram, but it's also pretty simple. What we learned from the MESSENGER mission was that the surface of Mercury is really enriched in sulfur and carbon, much more so than we thought was possible, because these are volatile elements. And Mercury's the closest planet to the sun. Had a hot violet. Why? Why would it have so much of these volatile components on its surface? And we think we have an answer for this now. And again, it's related to this pesky oxygen fugacity thing, because Mercury is a really, really reducing planet. It has almost no oxygen that's available to do anything, okay? If you look over here on the left, we'll just go through this really quickly. These are, again, these partition coefficients, how something goes either in the metal or in the silicate. And this is for the element sulfur, and this is for the element silica. And what you find is that when you get really reducing, like we think Mercury's mean oxygen fugacity was way over here, very, very reducing, that sulfur, which is usually siderophile and likes to go into metal, it's iron sulfide, right? It actually becomes what we call lithophile. It doesn't like the metal so much. Whereas silica is the opposite. Usually silica, it's lithophile. It likes to be in rocks. That's what rocks are made of, right? But when it's really reducing, it wants to be a metal. And so they kind of swap places, right? And so the idea is that when the core formed on Mercury, because it was so reducing, a lot of silica went into the core, and a lot of sulfur and carbon actually came out of the core, or didn't go into the core. They partitioned into the mantle. And so the reason there's so much at the surface is that the carbon, for example, relatively low pressure, carbon is graphite at that condition, it's very low density as graphite, and it floats to the surface. So you end up with this very graphite-rich flotation crust, just kind of like the anorthosite on the moon. It floated there, right? So that's why we have all this carbon on the surface. And the same thing for sulfur, is that you end up with a very sulfur-rich surface, because you had sulfur sort of within the silicate as it crystallized, but later on you had very sulfur-rich magmatism that poured out on the surface because you had all this sulfur available in the mantle. So again, We look at something that looks like an anomaly, and when we put the story back together, it looks like it's related to a magma ocean. I have one more slide. I realize I've gone a little long, and that's related to exoplanets. Because as we look out and we're searching for all these other worlds, what we're finding is that many of them, actually, a much larger proportion than you might expect, are so-called lava worlds. And there's a reason for that, because they're easy to find. They tend to occur around relatively dimmer stars. They can even be smaller objects, and they're really close to those stars. They have orbital periods of hours to days. And so they're so close that they're also tidally locked, which means that there's one side that's always like our moon. We're always seeing the near side of the moon because it's tidally locked, right? The rotation period of the moon is equal to its orbit around our planet. Same thing with these objects. So they always have one side that's facing their star, and they're really close to it. So they get really hot and they melt. And so one side is molten, but the other side is cool. And one of the neat things about it is that there's this region in between that can be quite temperate. And so they're actually planets where they're looking for the potential for habitability. Very different than our planet, right? But there's a region on these planets which is basically always in a temperate condition, and you might be able to have liquid water. Lots more to talk about there, but we don't have time today. And that, I believe, is it. So goodness gracious, thank you very much.
Thanks, Mike. Mike has agreed to take questions. There are the questions at Pigeonhole. Do you have
Ooh,
the
I
iPad for those?
have the
Does
iPad.
anyone have the iPad for those? I'll grab that. While we're doing that, we can also take some questions from the room. I will run you a microphone.
Mike, going back to your slide of
Here,
the Earth, you mentioned,
So people in the back. can
going back to your slide of the Earth, you mentioned that the differentiator was tectonics. When, how, and why did the plates form?
Yeah, that's a big question. And we don't know is the answer, actually. And so when plate tectonics formed is a really important question. And estimates for that range from anywhere around 3.2 or 3.5 billion years ago, the earliest potential evidence for that, to around 1.5 billion years. And so there's quite a bit of argument about when plate tectonics in its modern form might have started, because you can imagine other regimes of plate tectonics as well. For example, Venus probably has a regime, a stagnant lid regime, which means it has this lid that stays on it for a long time. The planet it starts to heat up underneath that, and it's heating more at the bottom, and so it becomes less dense, and it wants to overturn. And when it overturns, you have all this magmatism, and it replates the surface. Okay, so that's a form of tectonics. It's not like we have. So on planet Earth, probably I favor the older age, somewhere around 3.5 billion years. How it started exactly also relates to how it cooled. And so it may have also been in this stagnant lid regime. And so when it's hot, the crust that forms, the basaltic crust, like our oceanic crust today, it's too hot to want to sink. So what happens now is that crust is formed at mid-ocean ridges. It becomes about 6 kilometers thick. It's relatively hot when it does that. And as the crust forms, it spreads, called spreading centers. So every ocean has a spreading center right down the middle of it. As it moves away, it cools and it thickens. And on our planet, after about 200 million years, it reaches a point where it becomes more dense than the mantle beneath it. And that's when it starts to sink. And that's when the plates subduct, okay? And so that's kind of what needs to happen. You need to be in a thermal regime that allows that plate subduction to begin. And when that happens, well, you kind of kick off the modern style of plate tectonics. And again, there's a lot of dynamic arguments that go into that, and we don't know. The answer is we really don't know exactly when and why it started on our planet. We have ideas about it, but I can't point to a single answer for you.
So you have a question on Pigeonhole, which is how are we able to identify meteorites from different places, including Vesta?
That's a very good question. And for Vesta, the way that is done is we've got good spectroscopic data from the surface. Basically, it's reflectance data from the surface. And you can analyze that data and look at what the chemical composition of the surface is. And when we do that, we just get a really good match for a certain kind of meteorite called a eucrite. And a eucrite is one of the meteorites that we now associate with Vesta. Yeah.
Okay, we have, while I run the microphone over there, I'll ask the other question on Pigeonhole, which is how did Mercury get so reduced to begin with?
That's a very good question. We think that there was a range of meteorites, of primitive meteorites that formed the planets. And one of those is called the carbonaceous chondrites. They're very volatile rich. That Ryugu asteroid is like that. There's another class of primitive meteorites that are called enstatite chondrites. And these enstatite chondrites are very reducing, right? So when I say that, it means that all of the iron is either in metal, and the silicate parts of it, they have very little iron in them, okay? And they're quite reduced. And we think that there may have been a gradation in the inner solar system from much more reducing material in the inner solar system to progressively more oxidized material as you moved out. And this may be related to temperature and related to volatile content as well, okay? Because there's a temperature distribution. You go from hot in the interior to cool as you move out. And as you go out, eventually you hit a point, it's called the ice line, where you start condensing water ice, CO2 ice, other kinds of ices. And this is why outside of Mars, we have giant planets with gas, with like Jupiter and Saturn and Neptune. There's a lot of vapor and ice and ammonia around those planets, and because they're outside of that ice line. And so we just think there's this gradation in temperature, this gradation in volatile content, and this gradation in oxygen fugacity in the inner solar system. And you remember I showed you the picture of the HL tau, which shows the feeding zones. And so the idea is that Mercury's feeding zone was very close to the sun, and it was just feeding on very reduced material. So that's the simplest explanation.
Yeah, apropos of tectonics and so forth, is there information on viscosity and how it varies with temperature and pressure in the various segments?
That's a very good question. And there is information on that. Not as much as we'd like, especially as we go to higher and higher pressures and temperatures. Is one of the kinds of things that we do here, is make experiments at high pressures and temperatures on the minerals that we know that make up planets. And we try to measure their elastic properties. We try to measure, viscosity is tricky. We know elastic properties quite well, but measuring viscosity is hard at really high pressures and temperatures. So a lot of that comes from first principles calculations. So we do have an idea. They're probably pretty good ideas. And the models, the geodynamic models that we use to model things like plate tectonics and how it might get kicked off and what the convective timescales are, depend very much on things like the viscosity. Great question.
Any last questions? Okay. Well, thank you, Mike, for explaining how we were all started, all the planets of the solar system started as lava oceans, even though we wouldn't have wanted to live there now. Okay, let's thank Mike again.
Thank you.